State diagrams describe the behavior of state machines. I think it's helpful to link the state machine hardware structure with the state diagram, so let's do that first. We begin with the memory element called the state register. The present state is combined with the external inputs by the next state decoder to generate the next state to be developed into the state register. The clocking waveform allows time to advance once each clock cycle, and we can also force an initial state with the reset. The output decoder translates the present state into one or more, or possibly no, active outputs. We can also have the possibility of inputs fed forward directly into the output decoder to generate our outputs. All right, to make this a little bit more tangible, let's imagine that the state register consists of 3 bits. That is, it's composed of 3 D-type flip-flops. Now imagine we've just applied a reset pulse, and that reset is supposed to set the state register bits to all zeros. Now for 3 bits, we have 8 possible state codes. I'll just list out a few of those here. So again, 3 bits gives us 8 possible states. And in general, we would have 2 to the n possible states for n bits in the state register. Now this notion of the state whose code is 000 is represented by this ellipse, and I'll just use the decimal version of the binary number and call that 0. Now anytime the reset signal goes active, that forces us to this initial state. Now the present state is fed back to one of the inputs of the next state decoder. It's also fed forward to the output decoder, and let's imagine that we have outputs called C, D, and E specifically. Now suppose that when the output decoder sees this particular set of inputs, that it generates the output pattern 011. On our diagram, we then indicate that outputs D and E are active. So we simply write down those output names, and that implies that those lines are active in this state. Now the next state decoder is seeing a present state of 000. And let's imagine that regardless of the inputs, it always generates then, for this case, a next state code of 001. Clock edge comes along, and this value then gets sampled into the state register. We are now in a new state, and again I'll translate the binary pattern 001 into simply decimal 1. So this arrow denotes the transition from state 0 to state 1. It's called an unconditional transition because it did not depend at all on the inputs. All right. Now suppose that when the output decoder sees the pattern 001, it generates the outputs 000. That means we should leave this area blank. We don't indicate any active outputs. Now we see that the present value is fed back as 001, and let's give some specific inputs here called A and B. And let's imagine that these are both set to 00 at the moment. Now let's imagine 2 possible places that we will go if we are in state 1. That is, we can either head towards a new state called state 2, and let's imagine that we do this when A equals 0, and if we were to observe that A equals 1, then we would go from state 1 to state 3. All right, so if A is in fact 0, then the next state will be produced as 0, 1, 0. The clock edge comes along, and then we sample that value, and we are dropped then into state 2. However, if state 1 is, or excuse me, if input A is in fact 1, then the next state decoder is going to develop the output 0, 1, 1, which would, again, on the clock edge, cause 0, 1, 1 to get dropped into the register, and then we would be in state 3. Again, we could imagine some specific outputs that are supposed to be active when we are in fact in state 3. And so these are referred to as conditional transitions. Now we put a condition, we say take the path whose condition evaluates to 1. Now a little bit of a shorthand here is kind of nice and very common. We'll say let's imagine that we complement both sides of that equation. So we know that we have 0 complemented is in fact 1. So a shorthand for this is we write the condition as A complement, or A bar if you like. On the other side, that's simply A. So those two shorthands indicate either the condition A is 1 or A is 0. Let's put down a few more states and consider some other possibilities for transitions. So in this case, when we're in state 4, the transition depends only on the value of B and not on A. Now here's an interesting possibility. Back here in state 3, you don't necessarily have to go to another state. That is, you can use a self loop or a loopback, and this suggests that the way I've drawn this, especially if it's unconditional, that this would also be a type of trap state, because once we're in state 3, we can't get out unless you activate the reset. Now a self loop can also be associated with a condition, and this is how we go about waiting for something to happen. In this case, we say as long as B is 0, we'll stay in state 0, and then as soon as B becomes 1, we'll advance to state 1. In state 3, again, once we're in state 3, then we're stuck there forever. It's also important to realize that the next state decoder is generating the same pattern, 0, 1, 1, so repeated clocking of the state register means that we don't observe any change. Now let's consider a slightly more elaborate condition. When we take this path, say when A is 0, we go back to state 0, but if A is 1, then we need to consider what's going on with B. So if B was 0, we go to state 4, but if B is 1, then we go to state 5. So we see we've got a total of 3 exit paths from state 2. But in fact, you have actually 2 to the I possible exit paths for I inputs. So in principle, we actually have 4 possible exit paths from each state here. Now you'll notice that we've got a total of 6 states, and I think I'll stop drawing states at this point. But for 3 bits, we have a total of 8 possible states. So that suggests that we have 2 unused states. These are states 6 and 7. And let's consider some of the possibilities here. Now imagine that each one of these was outfitted with a self loop. Is that a good idea? Well, if the machine somehow accidentally gets itself into either of these states, then you're trapped in those states forever, to give the impression that the machine has just locked up for some unexplained reason. Likewise, if we were to simply say, well, once we're in either of these states, then we just bounce back and forth, that's probably also not a good idea. Perhaps a better idea is if we get it into one of these unused states, then we head back for the the initial state, and that gets us back into the main sequence.